Welcome to Digital Signal Processing Lab, and today we are going to conduct another experiment, and the objective of this experiment is to design a IIR filter. So here is the statement of the problem. So we have to design a digital Butterworth filter using a bilinear transformation to low pass and analog signal sampled at 2 kilohertz. The passband edge frequency is 200 hertz and the stop band edge frequency is 600 hertz. The ripple allowed in the passband is about 1.39938 decibel, and minimum stop band attenuation is 13.98 dB. We also have to get the frequency response of this particular filter, and we have to see whether we are able to meet the specification of the filter or not. So here we can see that if we have any analog low pass filter, then we are having a different prototypes to design an analog filters. And that filters may be your Butterworth filter, or it may be a Chebyshev filter, it may be an elliptic filter. Okay, so normally in the analog low pass filters, we can apply an input signals which are analog in nature, and we can get the output signal which will also be an analog signal, right? So to get this digital filter, okay, to design this digital filter, normally this analog low pass filter specification has to be transformed to its digital equivalent, right? So this transformation of transfer function from Laplace domain to the jet transform domain is done by using the bilinear transformation or impulse invariance transformation technique. So normally if we do this transformation, we will be getting the coefficient in the jet transform domain that will be defining our digital low pass filter. So we have to follow all this specification of your analog low pass filter, and then those specification we have to use to get the corresponding specification for your digital low pass filter, right? So normally in this case, our input signal will be converted to a discrete sequences by having a continuous to digital converters, okay? And then again, the output of this digital low pass filter will be our discrete sequences that we need to convert into your analog signal, right? So digital to continuous signal converter, right? So here we can see that if we have such analog filters, right? So corresponding digital filters will have this kind of frequency responses. So normally, if we have any digital filter, okay, and if its transfer function is denoted by Hej omega, then here you can see its frequency response curve. So normally the frequency response of your low pass filter will have this kind of characteristics. So here we can see that we are having a onto this x-axis, we are having the digital frequency, which is varying from 0 to pi, okay? And this omega p represents you the pass band edge frequency, and omega s will represent you the stop band edge frequency. Here we can see that in the pass band, we can see there must be a certain ripples, okay? Certain ripples that may be allowed, okay? So there will be a fluctuation of the gain of the filter within the pass band. It may be a flat gain, okay, but normally in the practical filters we don't get the flat bands, okay? So normally we can have a little bit variation in the gain, and we have to define what should be the maximum variation that may be allowed within this pass band, okay? So that we have to define. So here we can see that this maximum variations, right? So the minimum attenuation that may be possible is 1 minus delta p, right? So within the pass band, this gain should not fall less than 1 minus delta p. That we have to take care. Similarly, in the stop band, we have to define what should be the minimum attenuation that we have to achieve in the stop band. So stop band attenuation may be more than that, but it should not be less than the desired specification, right? So that we have to take care. So these are the important parameters that we need to take care, and based on the given specification, we have to design our filter. So normally you will find that if we take the Butterworth filter, okay, Butterworth low pass filter, then its specification, its system function generally defined by this particular equations, okay? And this is corresponding to your analog filters, right? So in the analog filter, you might be knowing that you will be having certain poles, and this transfer function will be given in the Laplace domain. So normally this specifications of your analog low pass filter must be transformed to its digital equivalent, okay? So here this analog filter, which is in the Laplace domain, has to be converted to its digital equivalent in the jet transform domain. So normally this will be done by using the various transformation techniques. So if we use the bilinear transformation as it is given in the problem that we have to use the bilinear transformation, then this Laplace variable s will be replaced by this particular equation. Okay, 2 upon ts 1 minus j to the power minus 1 divided by 1 plus j to the power minus 1, where ts is the sampling time. Okay, sampling interval. So that we have to follow, and then we have to make this conversion. So here we are not actually studying about the detail how this bilinear transformation will be done, because we have to perform the experiment onto the MATLAB. Okay, so we'll just see what are the specification and how it will be converted, and then how to perform this experiment onto MATLAB, right? So here we can see, because we have to convert this analog filter specification to HZ, and we know that this Z transform variable is defined is equals to R into e to the power j omega. So normally this S will be equals to j omega, which represents you the imaginary axis in Laplace domain. So this imaginary axis will be mapped to unity circle in the Z domain, right? And therefore you can have this Z equals to e to the power j omega, and this hz can also be written as hg omega. So normally you can see, because within this pass band there will be a ripples that may be allowed. So here you can see that this is showing you the maximum, this is your absolute gain. Okay, absolute gain of the filter. So normally this absolute gain, maximum gain that may be within this passband is 1 plus delta p, and the minimum gain that must be there within the passband is 1 minus delta p. So this minimum gain should not be less than 1 minus delta p. So normally we don't bother about the maximum gain, that you remember. Okay, this maximum gain can be 1, it can be 1 plus delta p, or it can be anything greater than 1 minus delta p, right? So we have to bother about this minimum gain, right? So if this minimum gain is 1 minus delta p, then within the pass band, the gain should not fall below this 1 minus delta p. That we have to take care. Okay, so here we can see this minimum gain in dB. If we calculate, we have to calculate this by using this formula, minus 20 log 1 minus delta p. Okay, so this will be in the dB. And the same thing we can also calculate if we put the magnitude of your transfer function h e j omega at omega equals to omega p. If we substitute, then we will be able to calculate at what frequency this may be at alpha p, means it is attenuation given in the dB. Okay, so this way we can this particular formula we can use for calculating the attenuation or frequencies at which this attenuation will take place. Now, similarly, we can have this stop band attenuation, right? So the absolute minimum attenuation at this particular stop band is delta S, right? So within this pass band, you remember that the gain offered by the filter should not be greater than delta S. It may be less than that, okay? It should be less than that, but it should not be greater than delta S. So minimum attenuation should be delta S, that you remember. Okay, so this way, if you see, we can have this type of filter specification. So within the pass band, the fluctuation in the gain of your digital filter may go from 1 minus delta p to 1 plus delta p, and within the stop band, this gain should be less than or equals to delta s, right? So this way we have to get the specification. So here we can see in the given problem, the pass band edge frequency, which is mentioned as 200 hertz, and stop band edge frequency is given as 600 hertz. Okay, these are the filter specification corresponds to your analog filters, so that you remember. And we have to convert this Butterworth filter into its digital equivalent by following the bilinear transformation method, right? So the sampling frequency mentioned is 2 kilohertz, you can see, and the ripple allowed in the pass band is given in the dB. So that value is alpha p, right? So this alpha p is equals to minus 1.98 dB, and the minimum stop band attenuation given in dB is alpha s, and it is equals to minus 13.98 dB. So now here we can just make the conversion of this all given filter specification, because we know that the relationship between the digital frequency omega with the analog frequency is given by this particular expression. Omega equals to analog frequency multiplied with the TS, right? So this omega can be replaced by 2 pi f upon fs, where f is the your analog frequency, right? And this fs denotes you the sampling frequency. So by following this relationship between the digital filter and digital frequency and analog frequency, we can calculate the corresponding values of omega p and omega s in digital domain, right? So here you can do this simple calculation, okay, and then you will be getting this omega p in digital domain equals to 0.2 pi and omega s equals to 0.6 pi. So now we can calculate by giving this specification. Ripple in passband is minus 1.98 dB. So here you can substitute 20 log HEJ omega p equals to minus 1.98, and that will be giving you this value mod HEJ omega p that you can calculate easily. So it will be coming out as 0.8. Similarly, 20 log HEJ omega s is equals to minus 13.98 dB. So if you calculate mod of HEJ omega s, it will be coming out as 0.2. So here you can see this transformation, right? So here we are going to have this filter. So our filter specification is transformed into this particular form. So this magnitude of our filter within this passband, okay, passband is varying from 0 to 0.2 pi, okay, so it will be in between 0.8 to 1, right? So here I have taken that key maximum frequency, maximum absolute gain is equals to 1, right? So this value will be varying from 1 to 0.8, right? Means 0.8 to 1. Similarly, in the stop band, this HEJ omega will be less than equals to 0.2. So now we have to implement the same thing onto the MATLAB. Okay, so let me go to the MATLAB, and here we can see how we can write this code. Okay, so here first of all we have to get all the this particular specifications of the filter, right? So here we can see first of all we have to take the sampling frequency, and that sampling frequency is equals to 2 kilohertz, okay, in the given problem. Here we have the passband edge frequency that we have to take from the input, okay, and we have to take the stop band edge frequency, and then we have to enter the passband allowed, okay, passband ripple that will be allowed, and then here we have to enter the minimum stop band attenuation which is allowed, right? So here I have just transformed this analog parameters into the equivalent digital one, right? So here we are calculating the omega p and omega s by just following the expression that I have just discussed, okay? So here you can see this particular expression. So this expression we have to implement there, okay, to get this omega p and omega s. So the one thing that we have just made the changes while doing the programming is I have just normalized this omega p by dividing it by the pi, okay? So here I am not just calculating omega, but omega p, but we are calculating omega p by pi. We are just normalizing this passband and stop band edge frequencies by pi. Okay, so here you can see this pi will be at the bottom of this omega p, and there we have in the program just we have taken these values, right? Here you can see 2 pi f pb divided by fs. So this pi will come to this bottom, okay, this denominator of omega p. So there in the program we have to write 2 into passband edge frequency divided by sampling frequency, okay? So the same thing I have written here, okay, you can see it is passband frequency, passband edge frequency multiplied with this factor 2 divided by the sampling frequency. Similarly, we are also calculating the stop band edge frequency, normalized stop band edge frequency, right? So here we have to get the order of the filter, okay? You remember that whenever we are designing a filter, we have to tell two important parameters. So what are those parameters? The parameters are what will be the order of the filter, and what will be the cutoff frequency of the filter, 3 dB cutoff frequency, right? So these two coefficients, these two filter parameters are very important, right? To get these two parameters, what is the order of the filter, and what will be the 3 dB cutoff frequency of the filter, we have to use this particular command, okay, MATLAB command, butod, right? So here we can type onto the MATLAB command window. If we write help and butod there, okay, if we write buttered, then you will be able to see what is this function, okay, and how to use this function. So here you can see this Butterworth filter order selection, right? So here you can see it will be giving you this two value, order of the filter and 3 dB cutoff frequency, right? So normally we have to give these 4 input parameters. So these are the pass band edge frequency, stop band edge frequency, ripple allowed in the pass band, and minimum attenuation in the stop band. So here we have to give the normalized frequencies. Remember, okay, we have to give the normalized frequencies, and these ripples will be given in the dB. So if we give these values, then we are going to get this order of the filter and 3 dB cutoff frequency of the filter, right? So that's why I'm using this particular command here. Okay, so if we use this, we will be able to get this values, right? So once we get this order of the filter and 3 dB cutoff frequency of the filter, if we use this butter command, okay, once we will be using this butter command, and if we give this two input parameters, order of the filter and 3 dB cutoff frequency of the filter, then we will be able to get this numerator polynomial and denominator polynomial of our filter, okay, of our digital filter, right? So this way we are going to get this digital filter specifications, right? Because in the digital filter, we do have a certain numerator polynomial and denominator polynomials. So those filter coefficient we need to get, right? So here we have to use this butter command to get those filter coefficients, right? And remember that in the butter command, we have to give this two input parameters. One is the order of the filter, and other one is the 3 dB cutoff frequency of the filter, right? So after getting this, we have to get the frequency response of the design filter. To get that, we have to first make the array for your frequency variable, right? So that array we have to get first. So here this omega we have started at from 0 to pi, okay, and the step size that we have taken is 0.01 into pi, okay, so that will be your step size. So here we have created the vector for your omega, okay, and for these values of omega we are going to calculate the frequency response. So here we have to use this particular command, okay, frequency jet command that I have already explained in my previous lecture. So here I have to give all those filter coefficients value B and A, and then we have to give at which particular frequency we have to calculate this frequency response, those W values we have to give, right? So because we have already defined this frequency vector, okay, of digital frequency, this is going to give you the entire frequency response from 0 to pi. Right. So here I have just displayed this values, okay, but order of the Butterworth filter and cutoff frequency of the Butterworth filter by using the disp command. Similarly, I have also displayed this numerator polynomial and denominator polynomials, right? Later on, we have to plot this figure, right? So we have to calculate the gain. So gain should be calculated in dB. So what we have to do is we have to take the mod of your frequency response H, right? So first we have to take the absolute value. To calculate the mod, we have to calculate the absolute value, and then we have to use this formula 20 log 10. Okay, then we have to give this absolute value of your frequency response. And then we have to plot this gain with respect to your this digital frequency, right? So to plot this frequency response, just I have taken the normalized value of the frequency. So, okay, W divided by pi. This way, we have to get this result, right? So here you can see if we execute this code, then we have to first enter all this given specifications. So we know that the sampling frequency in the given problem is 2 kilohertz, and pass band edge frequency of your low pass filter given is 200 hertz, and then the this stop band edge frequency is 600 hertz, and the pass band ripple, if you see in the problem, this is given as 1.938. Okay, so that we have to substitute here 1.938, 1.938, and then enter the minimum stop band attenuation is given as 13.98. so that you can give here. So here you can see now we have designed the filter. Okay, so we have designed the filter. So here you can see this is the passband edge frequency. So that we have already calculated. We got 0.2 pi. So because we are getting the normalized value, so it will be divided by pi. So here we are getting this result equals to 0.2. Then again, stop band edge frequency, we have got 0.6 normalized value. And to get this, to design this filter, the order of the Butterworth filter that we are getting is 2, and the cutoff frequency of the Butterworth filter is equals to 0.3542. So these are the filter coefficients, okay, numerator polynomials and denominator polynomials, right? So these filters coefficients will be we are getting for the given specification of the filter, right? So here you can see that the frequency response that we are getting. So here is the frequency response, right? So here you can see onto this x-axis we are having the digital frequencies, and onto this y-axis we are having the magnitude of your frequency response in dB, right? So here you can note down these values, right? So because we have to check whether we are getting these specifications or not, right? So here we can see these values, right? So here we can take this data tips, okay, and then you can check out this magnitude. So here you can see at 0.2, the maximum allowed ripple is minus 1.938. But here you can see that at x equals to 0.2, okay, at omega equals to, you can say omega equals to 0.2 pi. So this must be less than the allowed ripple, okay? So because here it is minus 0.312249, which is, if you see, it is more than minus 1.938, okay? So this is your at this point you can see that your specifications are over meeting, okay? So this is a good design as compared to the given specification, because we wanted that the maximum allowed ripple, okay, the maximum allowed ripple was minus 1.938, but we are getting better than that particular specification, because here the maximum attenuation is less than that value, right? Now here you can see at stop band edge frequency, if you see this parameter at this point, we are exactly meeting the stop band edge frequency specification, because in the problem, if you see at the stop band, the minimum stop band attenuation was minus 13.98 dB, right? So the same specification we are able to get at this point at 0.6. This attenuation, the minimum attenuation that we are getting is minus 13.98. And after that, you can see that this attenuation is rapidly increasing, okay? It is rapidly increasing. So here, after designing the filter, what we can see is we are able to exactly meet the stop band attenuation, it means stop band specification, but we are over meeting the pass band specification. So over meeting is good, okay? It should not be under meeting, right? So here we can see that this designed filter that we have got is better than what was our expectation, right? And one more thing that we can test here is, because we have got this, if you see this result, we have got this 3 dB cutoff frequency equals to 0.3542, right? So at this point, there must be a 3 dB loss, so that we can also check it out here. So 0.35 we have to see. So if you see here, okay, now at this point it is 0.35, okay? So 0.35, now we are getting 0.36. So here you can see it is almost equals to minus 3 dB loss. So this is corresponding to our 3 dB cutoff frequency of the filter. So that we are getting exactly right. So whatever we have designed. So hopefully you must have understood this filter designing concept, okay? So you remember that whenever we're designing digital low pass filter, then we cannot meet both these specifications, right? We cannot exactly meet the stop band attenuation as well as the stop band attenuation. So we can get either specifications, like we can either meet the stop band attenuation, stop band specification, or we can get the passband specification. You remember that one of the specification will mostly we are going to overmitting. Okay, so that specification we are mostly going to be overmit, right? So try to implement the filter using the MATLAB. Okay, and if you have any queries, if you have any doubt, let me know your queries by giving the comment into the comment box. So thank you for watching this video and try to implement onto the MATLAB. Thank you.